Greetings. In this video lecture, I'm going to discuss about the characteristic of functions, about the operation on function, I mean addition, subtraction, multiplication, division, combining function, and also identity function, the first one on the list. Now, functions can be characterized as an algebraic equation, as an analytical formula, as a set of ordered pairs, as a graph, as a table. But all of this that they are describing function, in reality they are all equivalent to one another with respect to the definition of function. So let's start with the definition of function. Function is a rule of correspondence between two non-empty sets, domain and range, such that each element in the domain set is paired with at least one element in the second set range. I will talk about domain and range later on also. Now, the word at least will divide the word of functions into two large groups. Is single-valued functions, and multi-valued functions. Now, the graph of a circle is considered as a multi-valued function. The reason the word function is attached to that is because it does follow certain discipline. For instance, in this figure, if x1 is paired with y1 and x1 is also paired with y2, but y1 and y2 are unique. So in other words, y1 and y2 are not random. They are not just coming from outside the set or from inside or somewhere else on this graph. That is the reason it is known precisely each of them are located, and we can use that one in our mathematical manipulation in more advanced courses. So for this reason, this is called multi-valued function. However, and also I have a schematic diagram here, as we can see is 1 to 2, which means one element in the domain of this function, in this multi-valued function, is paired with 2. Okay, now this multi-valued function, in this particular case, we can extract from that two implicit single-valued function. And I have gone through the algebraic process for that. You can see or pause and write it. And also here, when I took the square root of both sides for the algebraic manipulation, a square root of y squared is equal to absolute value of y, is not equal to y. And students do have difficulty with that. So I will be mentioning a few words about this before the end of the lecture. Okay, so so far so good. Now, the other thing that I have here that I would like to mention is that the graph of sine that we are all familiar with, Now, if I rotate this sheet of paper 90 degrees clockwise or counterclockwise, doesn't matter. If I rotate it clockwise and then reflect it, what I get here, let me just put it here, you can see. What I get here is the inverse relation of the graph of the sine function. Now, this is a multi-valued function. Again, for this x, for example, in the domain of this graph, in this, the y values are not random. They are these and these and these. There are infinitely many of them, but they are not random, and we can easily locate them where they are located. So this is example of multi-valued function. However, traditionally, traditionally, single-valued function is only considered as a function. So to be consistent with this tradition, and almost all the textbooks, not all, but most of the textbooks, they define function that way. So we drop from the definition I made, we drop the at least one to and replace it with maybe at least one and at most one, or uniquely paired with an element, indefinite article, with an element from the second set. Just this word an element will cause so many different kind of function to come up. How important it is to precisely digest the meaning and paraphrasing possibly the meaning of the definition. I may go over that also if the time permits. Now let me go to, so hopefully this is clear for you. Again, you can pause and you can look at it. Now let me see, I go to, oh, by the way, one thing I forgot to mention is that about the single valued function, let me mention it, is that when we take the derivative of a differentiable function, we always get another function. The value of the derived function at any given point x, is the slope of the tangent line to the graph of the function at that point. You see, in this, what I just said, is I did not mention that the slope of a tangent line will be at x comma f of x, or x comma y. I said at a point x. Why? Because the definition of the function being single valued, there is no need, because when you say the x here, the f of x will be unique. So there is no two possibility of f of x to be, so there is no need to mention that about the point. So we say for each point in there, the slope of a tangent line at the graph of the function at that point that we mentioned about x. It's just something aside. Now let's go about properties of functions. Now functions can be combined using arithmetic operation, addition, subtraction, multiplication, division. Also we can combine them through the other way is by composition of function. We can compose them. I will come to that also. I have it somewhere. Now here I go through one of these, and the rest of them logic follows exactly the same. Now here f plus or minus, which means two of them, I'm hitting two birds with one stone. Let's concentrate on plus part of it. F plus g of x equal to f of x plus g of x. Now, if you look at this and kind of memorize it in a parrot-like memorization, I can give a counterexample to show that this is not valid, is incorrect. Do you follow me? The way that I wrote it, the way I said it, is absolutely incorrect. Now my counterexample is here. So let f of x to be a square root of x, and let g of x to be x. I selected two easy examples. And I train my students also for that, to make their own example and seek for counterexamples. Now, we want to determine f plus g of -4. What is -4? So that means according to this setup, according to this recipe in a sense, will be f of -4 plus g of -4. But f cannot function, that's the right word in fact to say, cannot function with -4, because -4, if you give, is a square root of -4 when the index is even, is not a real number. So f of x is not in a sense defined in a set of real number, so it's empty set. So, but g of x is defined. What is g of -4 is -4. g of x equal to x. Now here we will end up with empty set plus 4. But empty set plus 4 is nonsense. If you have 3 apples and 2 oranges, what is 3 apples from 2 oranges? It's 3 apples from 2 oranges. You leave them alone. But here, empty set plus 4 is even worse than that in a sense, is a definitely nonsense. You cannot add empty set to 4. Two different things. So that means the counterexample I gave, this end up to be false. Now, what went wrong is that with function always goes domain and range. And domain is the set of all permissible values that the independent variable can possess. Now, when I'm talking about f plus g of x, I have to determine, because with the function goes domain and range, is that right? So I have to specify domain of that. And the domain of this, in order this to be a well-defined, is the intersection. Intersection, and we know about the concept of intersection in set. Intersection of the f and g, the domain of f and domain of g. Now, since we know not the domain of f plus g to be the intersection of them, then this will be a well-defined function, this one, and this operation is perfectly acceptable. So, in other words, nobody can give a counterexample. Now, the same logic and reason goes for the rest of them, exactly. So I don't have to go through that because of the shortage of time. Now, I guess I'm done with this. I go now to, I go to maybe I go to composition of functions. Now, composition of function is another way to combine functions to function and form a new function of them. Now, historically, Leibniz, a German mathematician, was spending sometimes days to look for the operation that carries the idea, carries the concept. And he was very good on that. Now, the students who will be taking calculus, they will see that, for example, dy over dx is a notation that Leibniz was using, and there's so many advantages. He carries so much idea of the concept. It helps so much to comprehend the concept. Now, the very same is true with this notation. Now, look at this notation. G and f are two functions, all right? Now, the domain of this function is going to come from the domain of g. All right, he says that. But function should have domain and range, and should have a rule of correspondence, and for each element in the domain you should have an element in the range. So the range of this g should fall into the domain of f in order this combination of functions can take place. If that doesn't happen, it may not take place. So I have different this will lead to different kind of situation about the composition of function, and I have them here written, and I go over them with your permission. Now, here, excuse me, there is no need for that now. Now, here, the G is mapping all this domain of G to its range, and f is dot, both of them are well-defined functions. Now we want to combine them. How do we combine as far as the composition of them is concerned? Now suppose that the range, as I have already shown that, the range of G here, the range of G must fall into the domain of f in order f to act accordingly. as a function. Now here, suppose that the range of G, by the way, if the range of G is going to be improper subset of the domain of F, then that is the best scenario. F has no problem because it covers entire domain of this, nothing more, nothing less. But most of the time this is not the case. What about if the range of G is going to be a proper subset of F? So I have drawn that one, so that means is a subset of F, but is a proper subset, so it doesn't cover the entire domain of F. Those that they are not covered, I put it by red color. But function must eat every element in its domain. So nothing should be left in the domain when we are talking about function. Now, how does this one work? Because in here I mentioned that the range of a G must fall into the domain of F. In this is falling, but how does now works? Y will be taking elements from the range of G, which is in its domain, and assign according to the rule of correspondence, assign elements in its range. Now here, what we will see, what happens to the rest of them? It looks like function is not eating all the elements of its domain because the domain of F now is concentrating on the range of G, which is a subset of that, which is a proper subset of that. So in that case, we say that the domain of F will be restricted. So those that they were outside, they are not going to be counted. In other words, you can think of the rule of correspondence of F remains same, but the domain of that is becoming a little bit shrink. It's a smaller, he has a kind of a new domain. But that domain that we say new is not new, is part of its own domain, but is a subset of that, is a proper subset of that. Then the other question we may ask, excuse me, Now, the other thing we may ask is that what about if the range of the G does fall sometimes outside the domain of F? What do we do in that case? Then the answer is very explicit and easy. In that case, you cannot compose the two functions. Now, the other question that may come, a schematic diagram helps a lot to fully comprehend the concept. The other one is that, what about if the range of G, part of it falls into the domain of F, part of it does not? What do we do then as far as the composition of function is concerned? This question has already been answered in reality. What do we do? The one that falls in the domain of F, that will be a subset, will be a proper subset of F, then F will be restricted to that proper subset. So that becomes a domain of F in a sense. But the rule of correspondence for F remains same. So in order to see if two functions are what you can combine them in this race, if you can go from here to here, and then, for example, you find the image of X under G, and that falls into the domain of F, then F takes that one and find the image of that with respect to this rule of correspondence. Then you can say I can go directly from domain of G directly to the range of G of F, by composing functions. I bypass the middle one. Provided we can do that, provided we have shown that. Now, composition of function has many applications in mathematics, in fact, and the derivative, when a student will be taking calculus, they will be seeing that also. And the other thing is that they will be mentioning soon about that, is that it's very good to use them to find out if two functions are inverse of one another. Because if you compose two functions together and the result will be identity, then we say, hey, yes, these two functions are inverse of one another. Okay, now I have made another example for the composition of function, algebraically. So for the just sake of the fun of it, I have composed the function with itself, and that ends up to be identity. Now, what I do is f of x equal to defined to be this. Then when I compose that one, this x of this will be replaced in the composition of them, will be replaced by this total to the right with all of this. And I have done that one, and I have gone through algebraic manipulation, and I definitely end up to be what? To be identity function. And then I also made, just to make sure, I made a few examples. For example, I selected 5. What is f of 5? Is 2 times 5 is 10, is 13. What is f of 5? 13 over, what is it? 3 times 5 is 15, 2 less 13. You said 13 over 13. All right? So when I put f in another word, when I put the 5, the identity also 5 comes out of it. So again, you can pause and you can look at it. I hold this for a few seconds if you have any concern about it. Okay, now let me see what will be in my list. Okay, now I go through the properties of identity function, which is also asked in that list. I have selected the first one in the list. Now, properties of identity function, I just read them what I have written for you, is that number one is that y equals f of x this is an analytical formula for identity function, analytical formula. Then its graph is always linear. The graph of the identity function is always linear. It passes through the origin, and the slope of that is always 1, always 1. Okay, then its graph is passed. Now, number D is that it plays the role of mirror image. That's interesting. It plays the role of mirror image between f of x and f inverse, which means when we draw the identity function and we have the graph of a function, we want to find the inverse of that graphically, that y equals to x, the graph of the identity function will be playing like the role of mirror. So the mirror image of that, the other side of that will be the inverse of that. And if the time permits, in fact, I have a short talk about that also. The rotation and reflection that I mentioned, I want to show why it works that way. 100%, you don't even need to use the mirror image as y equal to x to find the inverse of a relation or inverse of a function. Okay, then it can help to sketch the graph of inverse. I already mentioned it can help us to determine whether f and g are what are inverse of each other. I've already mentioned. So if you compose them together, f and g, and they end up to be identity, then we say yes, they are inverse of one another. So f circle g and then g circle f, if both of them produce identity, becomes like y equal to x, then yes, these two functions f and g are inverse of one another. And the other thing is that the set of domain and range of the identity function are the same. They have same domain and range. Okay, now let me go, if I may, to the absolute value I mentioned, because the students do have a little bit problem with that. So let me put it here. Oh, let me cover this one. It was covered, but I took it apart. Now, here, this notation asks a question. It says, what is the number that if you square it, you get 4? So the answer is simple, plus or minus 2. So the root of 4 is plus or minus 2, no doubt about it. We all agree with that. But this was causing a bit difficulty, because mathematics is very kind of meticulous subject. If there is any ambiguity, if anything can cause ambiguity, they immediately, mathematician make a definition to filter that ambiguity away. So In my time, I remember we didn't have something as a principal square root. And when in my graduate school, one of my professors said the exactly same thing. The principal square root looks like maybe, I don't know, not too long ago, maybe 50 years or something. But anyhow, since the principal square root says that a square root of 4 is not plus or minus 2. By a square root of 4, we always mean the positive root, which is plus 2. Then the question you ask is, hey, a square root of 4 does have two roots, plus and minus. Then what about if I am in need of the negative root of that? In that case, just put negative in front of this. That's all. Now look at this one. What is the square root of 4? By principal square root definition is 2. What does this negative makes it? Makes it negative 2. So that means that you are what? You are consistent with the principal square root. You have not violated that one. Okay, now let me say why why it is also the absolute value comes into the picture as far as why the absolute value is in the picture. Let me also go to that one. So I have already mentioned a square root of 4 plus or minus 2. Now, why a square root of x squared equal to absolute value of x and not equal to x? Now, a square root of x squared, the index is 2 in this case. Now, what is that one? You see, if I write it in the form of x squared to the power of 1/2, which means I write it in x to the 1/2 notation, then 2 times 1/2 is what? Is 1, so become x. Should be x. So why is not x? Because if it is x, then what happened? If x is negative 2, in this case, then these 2, if I write it in the form of 2 and 1/2, 2 and 1/2 goes, so the answer comes out to be negative 2. But the principal square root says that this notation is when you have like that, you always mean the positive root. You don't mean the negative root. But if I write it x, then x is, you see, x is not negative 2. So if a square root of x squared is x, then a square root of negative 2 squared should be negative 2, according to this recipe. But this is in violation of what? Of principal square root. And in order to overcome this violation, just put the x into the jail of absolute value. Then you have nothing to worry about, because absolute value will take care of it. Okay, then I thank you very much for the opportunity. I wish you all prosperity and happy life all the time, and please stay safe. So long.